humans have always wondered if our world was the only one. Ancient stories spoke of hidden realms, parallel heavens, and countless worlds beyond the stars. In Hindu cosmology, entire universes were said to be created and destroyed in endless cycles. Greek philosophers like Democritus imagined infinite worlds, some like ours, and others completely strange. Even medieval scholars wrestled with the thought that creation might not stop with just one universe. Fast forward to today, and those old myths sound less like myth and more like the first attempts to explain an idea scientists are now seriously considering. Modern physics has cracked open a possibility that feels both thrilling and unsettling. We might live in just one universe among countless others. For most of history, the idea of other universes lived only in myth and imagination. But as our tools sharpened and our questions grew bolder, those ancient dreams began turning into real scientific possibilities. For millennia, Aristotle's Earth-centered cosmos ruled human thought, a tidy universe with our planet at its heart. Then came Copernicus, who shattered that idea by proving the sun was the true center. Centuries later, astronomers believed the Milky Way was the whole universe, until Edwin Hubble found galaxies far beyond, racing away into the deep. That same pattern of surprise keeps repeating. Every time we think we've reached the edge, science pushes the boundary further. And in our time, just as scientists thought they'd mapped the limits of the observable universe, another idea began to take shape. One that quietly suggested our cosmos might be only a single layer in a vast cosmic hierarchy. The physicist behind it spoke of multiple levels of universes, each stranger and more expansive than the last. And unsettlingly, none of it was pure speculation. So the question shifts. It's no longer, is there another world out there? It becomes something far bigger. How many universes could there be? In the quiet town of Täby, Sweden, a young boy named Max grew up surrounded by two very different worlds. His father, Harold Tegmark, was a stern mathematician who believed everything, from snowflakes to galaxies, could be understood if you just found the right equation. His mother, Karen, was an artist and writer who filled their home with color, poetry, and open-ended questions. She saw patterns in brush strokes the same way Harold saw them in data. From them, Max inherited both precision and wonder. Dinner conversations in the Tegmark home could swing from abstract proofs to philosophical debates about reality itself. Between them, Max learned to see equations not as dry formulas, but as living shapes, almost like works of art. He was the kind of kid who'd stay up late sketching geometric patterns, while other kids played video games. Numbers fascinated him, not because they gave answers, but because they hinted at hidden symmetries, whispers of a grand design running through everything. To Max, mathematics didn't just describe the universe, it pulsed through it, like a secret language waiting to be fully heard. Quietly, he carried a question too daring to say out loud. What if math wasn't just a tool to measure the universe? What if math was the universe itself? That thought became his compass, quietly steering every choice he made. In school, while his classmates raced through equations just to get the right answers, Max lingered on the beauty behind them. Teachers often called him a dreamer, brilliant but distracted. He wasn't content with knowing how math worked. He wanted to know why it worked so perfectly, so universally. When others saw algebra, Max saw structure, an invisible architecture that seemed to shape everything around him. By the time he reached university in Stockholm, that obsession had become a quiet conviction. Reality itself might be mathematical. His papers began to draw attention, not for being flashy, but for the way they merged hard logic with unsettling questions about existence. Eventually, that curiosity pulled him across the Atlantic to the Massachusetts Institute of Technology, MIT, where the language of the universe was spoken fluently in chalk dust and late-night debates. In America, Max found himself surrounded by physicists chasing the deepest mysteries: the Big Bang, quantum mechanics, the fate of the cosmos. But while others tried to patch the equations of general relativity and quantum theory, Max kept returning to his childhood question. Maybe the universe is mathematics. From that seed grew one of the boldest ideas in modern science. He didn't just propose a new twist on reality. He built an entire framework of 4 levels of multiverse, each more radical than the last. But before Tegmark could argue for an infinite reality, the universe had to be revealed piece by piece. And that story began in California, in the year 1929. On the summit of Mount Wilson, perched above the haze and lights of Los Angeles, astronomer Edwin Hubble leaned into the eyepiece of the Hooker telescope. At the time, this was the most powerful telescope on Earth, a 100-inch giant of steel and glass. For years, astronomers had argued about the nature of faint, cloudy smudges scattered across the night sky, ghostly patches barely visible through smaller telescopes. Some thought they were clusters of newborn stars or swirling clouds of gas forming within our own galaxy. Others suspected they were something far grander, entire galaxies far beyond the Milky Way, each containing billions of suns like our own. This clash of ideas had reached its peak in 1920, during what became known as the Great Debate. Held at the Smithsonian's National Museum of Natural History in Washington, D.C., it wasn't just a scientific argument. It was a battle over the scale of existence itself. On one side stood Harlow Shapley, an ambitious astronomer from Harvard College Observatory. Shapley had spent years mapping the distribution of globular clusters, dense swarms of ancient stars that orbit galaxies like satellites. By studying their brightness and distance, he concluded that the Milky Way was far larger than anyone had imagined, stretching over 300,000 light-years across. To Shapley, this enormous scale left no room for other galaxies. Those faint smudges in the sky, he insisted, had to be small nebulae within our own galactic system. The universe, in his view, was vast, but self-contained. And Earth lay somewhere far from its center, humbling humanity's cosmic ego. On the other side stood Heber Curtis, an astronomer from Lick Observatory in California. Curtis had a keen eye for photographic detail and believed the night sky held far more than just the Milky Way. He had studied novae, sudden stellar explosions, within those cloudy spirals, and noticed they appeared much dimmer than novae seen in our galaxy. The only logical explanation, he argued, was distance. Those spiral nebulae weren't inside the Milky Way. They were far beyond it, each one a separate island universe containing billions of stars. But neither sides could offer solid proof. The technology simply wasn't there yet to measure those vast distances. So, the question remained unresolved, suspended between two possibilities. Was the Milky Way the grand total of creation, or just one speck in an endless cosmic sea? And the answer, as it turned out, came from Edwin Hubble, a former lawyer turned astronomer who worked at the Mount Wilson Observatory in California. Unlike many of his contemporaries, Hubble didn't stumble onto the problem by accident. He set out to solve it. He knew about the Great Debate and wanted hard evidence to decide who was right. For that, he needed better data, something only the Hooker telescope, then the largest in the world, could provide. Hubble's weapon of choice was a type of star called a Cepheid variable. These stars pulse in brightness at regular intervals, and that rhythm can reveal how bright they truly are. By comparing their known brightness to how dim they appear from Earth, astronomers can calculate their distance. A method first pioneered by Henrietta Swan Leavitt at Harvard in 1908. Her discovery turned Cepheids into cosmic mile markers, and Hubble used them to measure one of the most famous smudges in the sky, the Andromeda Nebula. Night after night, he photographed Andromeda on glass plates, marking faint points of light that changed brightness. Then, one evening in October 1923, he scrawled 3 letters on his plate, short for variable star. That tiny note would rewrite the universe. The Cepheid's distance showed that Andromeda wasn't a small cloud within the Milky Way. It was a galaxy millions of light-years away, far beyond our own. Suddenly, Curtis's island universes were real. The scale of existence exploded overnight. What once seemed like a single grand city of stars was revealed to be part of a vast cosmic archipelago, each galaxy containing billions of suns. Newspapers at the time called it the greatest discovery in astronomy since Copernicus. Hubble became a reluctant celebrity, but to him, the thrill wasn't fame. It was the realization that the universe had no obvious boundary. And he didn't stop there. Using the same telescope, Hubble began measuring redshifts, the stretching of light toward longer wavelengths as galaxies moved away. To his surprise, he noticed a pattern. The farther a galaxy was, the faster it receded. This relationship became Hubble's law, published in 1929. It meant the universe wasn't static, it was expanding. Space itself was stretching, carrying galaxies apart like raisins in rising dough. The shockwaves of that finding reached all the way to Albert Einstein, who had earlier inserted a cosmological constant into his equations to keep the universe stable. When Hubble's data arrived, Einstein visited Mount Wilson himself. Looking through the telescope, he reportedly murmured, "I now see the necessity of a beginning." Later, he called his earlier assumption the greatest blunder of his career. The message was clear. The universe was vast beyond measure, and it was still growing. Like dots painted on the surface of a balloon, every galaxy drifted away from every other as the balloon inflated. There was no privileged center and no edge, only endless expansion. Suddenly, the cosmos had a history. If everything was moving apart, then at some earlier time, everything must have been closer together, compressed into a hot, dense beginning. That beginning became known as the Big Bang, the moment when the entire universe burst into being from an unimaginably hot and dense state. But for decades, the idea split the scientific world. Many astronomers found it hard to believe that everything, space, time, and matter, could come from nothing. Some clung to a different vision, called the steady-state theory, proposed in 1948 by Fred Hoyle, Hermann Bondi, and Thomas Gold. They argued that as the universe expanded, new matter continuously formed to fill the gaps, keeping its overall density constant. The cosmos, in their view, had no beginning and no end. It simply was. Eternal and unchanging on the largest scales. The Big Bang camp saw things differently. To them, the galaxy's outward rush suggested a past explosion, an origin. But while the math and Hubble's expanding universe hinted strongly at a beginning, the evidence was still circumstantial. There was no smoking gun, no lingering trace of that first fire to prove it had ever happened. For nearly 2 decades, both camps fought for dominance, trading papers, radio broadcasts, and even insults. Ironically, the term Big Bang itself was coined mockingly by Fred Hoyle during a BBC radio show in 1949. He never meant it as praise. By the early 1960s, the question was reaching a breaking point. Cosmology had become a quiet battleground of ideas, and the race for proof was on. And then came an unexpected twist. Just a few miles apart, 2 groups were unknowingly closing in on the same answer. At Bell Labs in Holmdel, New Jersey, 2 young radio engineers, Arno Penzias and Robert Wilson, were fine-tuning a massive, horn-shaped microwave antenna originally built for satellite communication experiments. Their goal was simple: eliminate all background noise from their receiver. But no matter what they did, a faint hiss persisted. A low, steady static that came from every direction in the sky, day or night. They were meticulous. They checked every connection, recalibrated the system, and even climbed inside the horn to clean out what they jokingly called white dielectric material, pigeon droppings, in other words. Yet the hiss remained. It wasn't interference from the city or the sun, nor from any known source on Earth. It was as if the universe itself was whispering. Meanwhile, across the river at Princeton University, physicist Robert Dicke and his team, including a young Jim Peebles, who would later win the Nobel Prize, were working on a very different project. They were trying to detect the faint afterglow of the Big Bang, a remnant heat that should still bathe the cosmos in microwave radiation. Dicke had predicted that if the universe began in a fireball, that leftover light would have cooled over billions of years to just a few degrees above absolute zero. But it would still be there, spread evenly across the sky. The 2 groups didn't know about each other's work until chance intervened. Penzias and Wilson, frustrated by the mystery noise, called an astronomer friend at Princeton, who realized what they had stumbled upon. When the news reached Dicke's lab, he reportedly turned to his students and sighed. That faint hiss wasn't a glitch. What Penzias and Wilson had stumbled upon was the cosmic microwave background, the afterglow of creation itself. This radiation was a fossil imprint, from when the universe was only about 380,000 years old, long before the first galaxies or stars. It was the universe's baby picture, preserved across the entire sky. The cosmic microwave background confirmed that the universe had a beginning. But when scientists began mapping it in detail, a strange paradox appeared, one that didn't quite add up. In the late 1980s and early 1990s, satellites like NASA's Cosmic Background Explorer scanned the sky with unprecedented precision. What they found was remarkable. The radiation's temperature was almost perfectly uniform, just 2.725 Kelvin, only a few degrees above absolute zero. No matter where astronomers looked, toward distant clusters or the opposite end of the sky, the numbers came out nearly identical, differing by less than 1 part in 100,000. At first, this smoothness seemed beautiful, even poetic, as if the early universe had been a perfectly balanced newborn. But it soon became deeply confusing, because if the universe had truly begun in a hot explosion, it should have expanded unevenly, leaving behind regions with wildly different temperatures. Light, and therefore heat, can only travel so fast. The observable universe today spans roughly 93 billion light-years, yet only 13.8 billion years have passed since the Big Bang. That means distant regions are so far apart that light from one side could never have reached the other in time to even out their temperatures. Put another way, there hadn't been enough time for the universe to mix. It was as if parts of the cosmos that were never in contact somehow agreed on the same temperature down to the tiniest decimal. This became known as the horizon problem, and it wasn't a small detail. It struck at the heart of the Big Bang model. For those distant patches of sky to look so similar, they must have once been part of a smaller, denser region, capable of equilibrating before being stretched apart by cosmic expansion. But the standard Big Bang theory didn't allow for that. The math just didn't fit. Physicists started to grasp how bizarre this was. Imagine 2 classrooms, one in New York and one in Tokyo. Each teacher gives the students a complex assignment and forbids them from communicating. When the homework is collected, every single answer, including the mistakes, is exactly the same. That's what scientists were seeing across the sky. Enormous regions of space that had somehow coordinated their answers without ever having the chance to talk. Something hidden had to connect them. Some event or mechanism early in the universe's history that allowed distant regions to share information before being torn apart by cosmic expansion. Whatever it was, it had to happen almost instantly after the Big Bang, and had to be powerful enough to shape everything that followed. That's when a young MIT physicist named Alan Guth, working late one night in 1979, stumbled upon an idea that would not only solve the horizon problem, but rewrite our understanding of reality itself. Guth, then a struggling postdoctoral researcher, asked, what if the universe itself went through a burst of faster-than-light expansion in its very first instant? In his notes, he underlined the phrase, spectacular realization. That spark became the theory of cosmic inflation. In less than a trillionth of a second, the universe ballooned outward exponentially. Space itself didn't just grow, it exploded in size, carrying matter and energy along with it. inflation neatly solved three deep puzzles. It explained why the universe looks flat and balanced rather than curved or chaotic. It solved the horizon problem. The entire visible universe was once a tiny, tightly connected region, allowing temperatures to equalize before being stretched across billions of light years. And it explained why hypothetical magnetic monopoles, predicted by particle physics, are nowhere to be found. They were thinned out by inflation's rapid growth. Imagine kneading dough filled with small air bubbles. Place it in an oven, and the bubbles stretch into a uniform, smooth loaf. Inflation was the cosmic oven that smoothed the universe into the flat, even space we see today. But bold ideas in physics only survive if nature leaves a fingerprint. Guth predicted that quantum jitters in the newborn universe, tiny subatomic fluctuations, would be blown up to cosmic size, etched as ripples across space-time. For years, the CMB looked smooth. But in 1992, NASA's COBE satellite finally detected the anisotropies, minute temperature variations, 1 part in 100,000. George Smoot, who led the team, remarked, "If you're religious, it's like looking at God." Later missions, WMAP in the 2000s and Planck in the 2010s, refined the measurements, revealing a universe astonishingly flat and seeded with the precise Gaussian ripples inflation had predicted. The implication was staggering. The cosmos might not just be vast, but endless. Max Tegmark saw all of this unfold behind his chalkboard at MIT. Equations scribbled across the black surface as he traced the story of the cosmos in his mind. He watched the discoveries stack like chapters in a single epic. First came Hubble, whose telescope on Mount Wilson revealed that the Milky Way was not the entire universe, but just one of billions of galaxies scattered across an almost unimaginable expanse. That expanded view of space raised deeper questions. How had it all begun? Then Penzias and Wilson offered a clue: the cosmic microwave background, a faint afterglow left over from the universe's fiery birth. Suddenly, the universe had a beginning, a tangible imprint of its earliest moments. Yet the newborn cosmos held mysteries. Its radiation was astonishingly smooth, a puzzle Guth would later address, by proposing that the universe underwent a mind-bogglingly rapid inflation in its first instant. Guth connected distant regions that had no way to communicate, smoothing out the cosmos and giving it a structure that seemed almost intentional. Satellites like COBE, WMAP, and Planck later mapped these faint ripples with exquisite precision. The universe, they showed, was not tangled or curved, but flat, vast, and seemingly infinite. Each discovery flowed into the next. Hubble revealed scale, Penzias and Wilson revealed origin, Guth explained structure, and the satellites confirmed the pattern. And if the universe was flat, stretching endlessly without curving back on itself, then a startling possibility emerged. What we can see is only a tiny patch of something truly infinite. From behind his MIT chalkboard, Tegmark noticed a profound implication hidden in the numbers. Within the observable universe, the number of possible atomic arrangements, about 10 to the power of 118, was staggeringly large. Yet in an infinite cosmos, that number is tiny. Somewhere out there, another patch of space must exist that mirrors our own, down to the smallest detail. Somewhere, an exact copy of this universe might be waiting, a silent twin among countless possibilities. Tegmark liked to make this mind-bending idea simple. He often joked about socks to explain it. Imagine you wake up and reach for a blue pair, just like you always do, without thinking. In another part of the universe, far beyond what we can see, there's another version of you doing the same morning routine, but with a tiny difference. This time, you reach for a red pair instead. Travel even farther, and you'll find a version of you who never bought socks at all. And somewhere even more distant, there's another you living the exact same life. Same memories, same thoughts, unaware that you're both out there, like cosmic doppelgangers separated by unimaginable distances. Every small choice you make, every tiny change in your life, happens somewhere in this endless, infinite cosmos. That's the strange rule of infinity. It doesn't just allow possibilities to happen, it guarantees them. Like rolling a pair of dice over and over, forever. Every number combination, doubles, triples, every possible sequence will appear again and again, endlessly, no matter how unlikely. Now, scale that up to the universe. Every arrangement of atoms, every choice you've ever made, every star, every planet will repeat somewhere in that infinite space. And in that endless repetition, Tegmark glimpsed something even bigger. Infinity didn't just create copies of our universe, it hinted at a deeper structure, layers upon layers of reality, stretching beyond anything we could imagine. In 2003, Tegmark laid out all of these for the public in Scientific American. Somewhere out there, he wrote, there's a copy of you differing only by the color of your socks. Don't underestimate the joke. Beneath it was a radical truth. Cosmology's march from galaxies to the Big Bang to inflation had built a ladder straight into the multiverse. And Tegmark's first rung on that ladder was what he called the Level 1 multiverse. Imagine you flip a coin 100 times. In our observable universe, you might get a sequence like this. But in an infinite universe, every possible sequence of flips exists somewhere else. That means there's a region of space unimaginably far away, where the sequence came out all heads, and another where it matched your exact flips perfectly. Now scale that up to planets and people. In our observable patch of the universe, you're sitting here reading this explanation. But far beyond the 46 billion light-year horizon, there's another region where the same laws of physics apply, but the initial conditions after the Big Bang were slightly different. In one of those regions, there's an Earth almost identical to ours, with a person almost identical to you. The only difference is that maybe they're reading this explanation in Spanish instead of English. In another region, there's an Earth where dinosaurs never went extinct and humans never evolved. This is Tegmark's Level 1 multiverse. Infinity doesn't just suggest their existence, it guarantees them. Level 1 doesn't rely on exotic or untested physics. It comes straight from the idea of an infinite cosmos stretched by inflation. The simplest doorway into the multiverse opens here. No leap beyond known science, just the acceptance of infinity itself. But for Tegmark, infinity wasn't an end point. It was just a beginning. If space could spawn endless copies of us simply by stretching, what else might physics allow? And why should the rules themselves remain fixed? He couldn't leave that question alone. From the calm infinity of level 1, his mind turned towards stranger possibilities. And it is here that we shift from the gentle infinity of repetition to something far more radical. Moscow, 1948. The city was grey with ideology and cold with control. Stalin's portrait hung over every classroom, and curiosity was something you learned to hide. In the Soviet Union, science was not a search for truth. It was a servant of the state. The universe, they said, was eternal, stable, and perfectly knowable, just as Marx had imagined. No creation, no expansion, no Big Bang. The cosmos itself had to obey the party. But Andrei Linde didn't quite fit inside that box. He was the kind of boy who asked too many questions, who filled the margins of his notebooks with symbols that didn't belong to any lesson. His teachers wanted tidy answers. He wanted the unknown. Late at night, while Moscow slept, he read everything he could find, often smuggled papers, copies of Western journals passed in whispers from hand to hand like contraband. Those pages spoke of galaxies beyond the Milky Way, of light from the universe's beginning, of ideas his textbooks pretended didn't exist. To Linde, they weren't just papers. They were glimpses of freedom, proof that the universe was far larger than the borders drawn around him. By the 1970s, Andrei Linde had made his way into the heart of Soviet academia, Moscow State University. The place was a paradox, brilliant minds trapped in a system that distrusted curiosity. Lecture halls were filled with chalk dust and cautious ambition. The professors spoke carefully, measuring each word, but between the lines, a quiet rebellion stirred. Linde found himself among other restless young physicists who wanted more than official doctrine. In whispered conversations over weak tea, they traded rumors about discoveries from the West. Hubble's galaxies racing away from each other, proof that space itself was stretching. Then came the story of 1965, when two engineers in New Jersey, Arno Penzias and Robert Wilson, accidentally picked up a mysterious hiss. The leftover heat of creation itself. The evidence was undeniable. The universe had not always been. It had a beginning, a fiery birth that no Soviet textbook dared to mention. Then, in 1981, news from across the Iron Curtain made its way to Moscow's underground circles. Alan Guth, a young physicist at MIT, had published a paper proposing something bold: cosmic inflation. According to his idea, as we already discussed, in the first unimaginable instant after the Big Bang, about 10 to the minus 32 seconds, space ballooned faster than light. That single burst could explain almost everything. Why the universe looked so smooth, why it appeared flat, and why distant regions shared the same temperature. For Linde, it was thrilling and frustrating. The equations were elegant, but when he worked through Guth's model, he saw a fatal flaw. Inflation ended too abruptly. The universe, according to Guth's math, would have been left scarred with defects, dense knots of energy that didn't exist in the sky we see. It was like a brilliant story that stumbled at the final page. The theory needed a smoother ending, and Linde couldn't stop thinking about how to fix it. He couldn't let it go. The flaw in Guth's theory gnawed at him like a loose thread he couldn't stop pulling. Night after night, Linde stayed in his small Moscow apartment, working by the light of a single lamp, pages scattered across his desk. He ran through every possibility, searching for a version of inflation that could fix the broken ending without breaking the story itself. And then one night, a thought began to take shape. What if inflation didn't have to stop everywhere at once? What if, instead of a single, synchronized event, it ended in patches, like boiling water, where some bubbles burst while others keep expanding? The idea refused to leave him. He followed it, tested it, and pushed it further. Slowly, the picture sharpened. By 1983, Linde had his breakthrough. It wasn't luck or a sudden flash. It was the result of years of persistence. He called it chaotic inflation. Guth's model had lit the first spark, but Linde turned it into a firestorm. Inflation, he realized, wasn't a one-time event that came and went. It could keep happening eternally across different regions of space. Some pockets would cool and form universes like ours, while others would keep expanding, endlessly creating new ones. Inflation didn't end. It multiplied. Think of the universe not as a single firework, but as a boundless ocean of energy. In this ocean, bubbles constantly form where inflation slows down and stops. Each bubble is a universe. Each one sealed off, pushed away from its neighbors by the relentless growth of space itself. Inside those bubbles, as the energy cooled, the rules of reality locked into place. And here's the leap. Those rules didn't have to be the same everywhere. One bubble might have stronger gravity, another a different set of particles, another something stranger still. Linde wasn't just tweaking the Big Bang. He was proposing something far more radical. A cosmic landscape made of endless bubble universes. In his view, inflation didn't stop everywhere at once. It ended locally, here and there, like bubbles forming in an infinite pot of boiling water. Each bubble marked a new universe, born in its own burst of expansion, with its own version of a Big Bang inside. Inside one bubble, the conditions might look like ours: galaxies, stars, life. In another, gravity could be stronger, or atoms might never form. Some bubbles could collapse in an instant. Others might stretch and cool into vast, stable worlds. There wasn't just one cosmos anymore, but a frothing sea of universes, all budding off from an eternally inflating space. No one could say how many existed. There could be trillions, or an infinite number, each sealed off from the rest by the ever-expanding space between them. From our perspective, we could never cross that divide, or even see beyond our own bubble's edge. Yet according to Linde's math, the process never stopped. Somewhere, right now, new universes are still being born. For Linde, trapped in the ideological confines of the Soviet Union, the metaphor was sharp and personal. His own world felt like a closed bubble, sealed by politics and censorship. So when he finally emigrated to California in the 1990s to teach at Stanford, it felt like stepping into another universe entirely. Freer, brighter, buzzing with open debate. His life, in a way, mirrored his theory. A multiverse of worlds, each with its own rules, each shaped by its own beginning. But Linde's idea opened a deeper question. If these bubble universes truly exist, are they just variations of ours, like Tegmark's repeating worlds, or do they follow entirely different laws of physics, where reality itself rewrites its script. Back then, most physicists brushed off the idea as too wild to test. But then came a surprising ally from an unexpected corner of theoretical physics. In the 1970s, a young Bronx plumber-turned-physicist named Leonard Susskind was wrestling with one of the deepest puzzles in science. What if matter isn't made of tiny points, but vibrating loops of energy? That question became the seed of string theory. Each string could vibrate in countless ways, like a cosmic violin, playing different notes. And each vibration created different kinds of particles, forces, even dimensions. By the early 2000s, string theory took a shocking turn. Instead of describing one neat, unified universe, it allowed for roughly 10 to the power of 500 possible vacuum states. That's a number so vast, it makes the number of atoms in the observable universe look small. Each state came with its own physics. Gravity could be stronger or weaker, space could have more or fewer dimensions, time could flow differently. It was as if the universe wasn't one song, but a massive symphony of possible tunes. Each one a different cosmos, each playing in its own bubble. Some were familiar, some utterly alien. Together, they formed what physicists began to call the multiverse landscape. But the idea split the physics community. Leonard Susskind embraced the landscape, calling it a natural outcome of the mathematics. Steven Weinberg, a Nobel Prize-winning physicist, saw it as a practical explanation for one of the biggest mysteries: why the cosmological constant in our universe has a value that allows galaxies and life to exist. In a multiverse of many bubbles, only some would have the right conditions, and we naturally find ourselves in one of those. Others, however, recoiled. David Gross, another Nobel laureate, dismissed the landscape, declaring, "This is not physics, it's giving up." For him, science had to make concrete predictions, not multiply universes without proof. Lee Smolin warned that a multiverse stripped physics of its defining feature: falsifiability. If every possible universe exists somewhere, then no observation could ever disprove the theory. The debate grew fierce, echoing old philosophical battles about whether reality is discoverable or whether we are trapped like prisoners in Plato's cave, staring at shadows on the wall. Through all of this, Max Tegmark watched the chaos unfold like a librarian in a room full of shouting geniuses. String theorists argued about extra dimensions, cosmologists debated eternal inflation, and philosophers questioned whether any of it could ever be proven. But Tegmark didn't pick a side. He stepped back, observing the swirl of ideas, and decided to organize the madness into something people could actually understand. He proposed a hierarchy, a layered map of reality that tried to make sense of the chaos. Level 1, Tegmark said, was the simplest and closest to home. Think of it as our own universe, stretched to infinity. Beyond the edge of what we can see, there could be more galaxies, stars, even versions of you, just born in slightly different circumstances. Maybe in one, you wore blue socks today instead of yellow. The rules of physics stay the same everywhere. Only the starting conditions differ. Level 2 went deeper. This was the realm of Andrei Linde's eternal inflation and Leonard Susskind's string theory landscape. Here, whole regions of space stop inflating and form bubble universes, each sealed off from the others. But these aren't copies of ours, they're fundamentally different worlds. The speed of light, gravity, even the number of dimensions could vary. One bubble might have no stars at all, another could be ruled by entirely different chemistry. The difference between level 1 and level 2 is the difference between rolling dice versus changing the dice themselves. Level 1 tweaks the outcomes within the same game. Level 2 invents new games entirely, each with its own rules. To Tegmark, this wasn't science fiction. It was a structured way to understand the vastness of existence, a cosmic filing system for infinity itself. Yet as he placed these ideas neatly onto shelves, Tegmark noticed a gap. Inflation and string bubbles could explain why different universes might have different constants, but they didn't touch the strangest part of all: the way quantum mechanics seems to allow every possibility to exist simultaneously. That puzzle had been sitting in plain sight since 1957, in the thesis of a young graduate student named Hugh Everett. And it was to Everett's ignored idea that Tegmark and the multiverse would turn next. Autumn sunlight slanted through the ivy-covered walls of Princeton, warming the stone courtyards where young physicists argued in hushed voices. Chalkboards were crowded with equations, and cigarette smoke hung thick in seminar rooms. It is the late 1950s. The war had ended, but another kind of tension filled the air, one made of politics, secrecy, and the race to understand the atom before the other side did. Inside those lecture halls, quantum mechanics ruled. For 30 years, Erwin Schrödinger's elegant equation had described the strange, wave-like behavior of particles. It was neat, precise, and completely deterministic. If you knew a system's wave function at one instant, you could calculate its entire future. But there was a catch everyone tried to ignore. The students were taught that the wave function didn't actually keep evolving forever. The moment you measured it, something strange happened. It collapsed. All the smooth probabilities suddenly snapped into a single outcome, like a dice coming to rest on one number. That collapse wasn't in Schrödinger's math. It was a rule tacked on later, a patch to make theory match experiment. In the quiet hallways of Princeton, this inconsistency was like a hairline crack in a flawless crystal, small, almost invisible, but impossible for the sharpest minds to ignore. Hugh Everett was 26 years old, working under the legendary John Wheeler. He asked a blunt question. If the mathematics of quantum mechanics never collapses, why should reality? What if the wave function described everything? Not just particles, but measuring devices, observers, even the universe itself. If you take Schrödinger seriously, then collapse never happens. Every possible outcome continues on, branching into its own thread of reality. The cat isn't alive or dead. It is alive in one branch, dead in another, both real, both unfolding. I know some of you probably wouldn't love it if I showed the full technical form of Everett's equation, so let's keep it simple. Normally, we think it lands on heads or tails, but Everett said, what if it's both? Not just in theory, but in reality. Every time you flip the coin, the universe itself splits. In one branch, you see heads. In another, you see tails. Both outcomes exist, but in separate, non-communicating worlds. Extend that to everything, every decision, every particle interaction, every quantum event. Each one causes a new branch to unfold. Somewhere, another version of you made a different choice, spoke a different word, or didn't exist at all. You don't feel the split, because each version of you follows its own thread, unaware of the others. To Everett, the universe wasn't a single film reel with one story. It was an ever-branching forest of realities, all growing from the same root, each equally real. There was no collapse, only constant division, endless and unstoppable. Everett carried his radical idea to Copenhagen, where the elder Niels Bohr still guarded the orthodox interpretation of quantum physics. Bohr believed physics had to give a single, definite result, something you could measure, record, and share. Everett's proposal that the universe constantly split into countless invisible copies sounded like science fiction. Bohr listened with his usual stern patience, then waved the idea away. The Copenhagen school dismissed Everett, and with it, the many worlds interpretation. Frustrated, Everett abandoned academia. He joined the Pentagon's think tanks, working on nuclear war planning at the height of Cold War tensions. There is a grim irony in that career choice. In his equations, worlds branched endlessly, but in his day job, he was calculating scenarios where the world could end in a single flash of atomic fire. He drank heavily, grew disillusioned, and died in 1982 at just 51. In some alternate branch of reality, perhaps Everett lived to see his rebellion vindicated. In ours, he was ignored during his lifetime. For 2 decades, his paper gathered dust. Then, in the 1980s, physicists like Wojciech Zurek revived it through the concept of decoherence. Decoherence explained why Everett's branching universes don't interfere with one another. As soon as a quantum system interacts with its environment, air molecules, light, or even a measuring device, the delicate superposition breaks apart. Each possibility continues on its own trajectory, unable to recombine. Think of ripples in a glass of water, perfectly interfering. Now toss in sand, the ripples scatter instantly, fragmenting into separate puddles that can never meet again. That's decoherence. It gave Everett's ghost scientific flesh, and experiments like the double-slit test began to look different. In the Everett view, the electron truly goes through both slits, but in separate universes. We only ever experience one branch, but the other is just as real. Or think of it like listening to an orchestra. When all the instruments play together in harmony, the sound waves blend into one beautiful song. That's coherence. But the moment someone opens a door to the noisy street outside, the music gets drowned out. The notes are still there, technically, but the interference from everything else, the chatter, the wind, the cars, separates the sounds so completely that you can no longer hear the orchestra as one. That's what happens in the quantum world. When particles interact with their surroundings, air, light, atoms, heat, they lose that delicate harmony. The wave function doesn't collapse, it just decoheres, splitting into outcomes that can no longer hear or influence each other. Tegmark loved this analogy. To him, decoherence wasn't mystical, It was practical. It explained why we don't see cats that are both alive and dead, or coins that are both heads and tails. Each version of the world keeps playing, but in its own silent concert hall, separated forever from the others. So when Tegmark read Everett's work decades later, he didn't see a crazy fantasy. He saw physics doing what it always does, following its own logic to the end. If the math says all outcomes persist, then somewhere, somehow, they do. Tegmark's genius wasn't just in understanding the physics, but in framing it. He placed Everett's idea in his grand system of multiverse levels. Level 1 was the infinite universe, where only initial conditions change. Level 2 was the realm of inflationary bubbles, each with its own constants. Level 3 became Everett's world, not different regions of space, but different outcomes in quantum time. Here's the key detail. Level 3 doesn't add universes on top of levels 1 and 2. It doesn't multiply infinities unnecessarily. It simply shows that within any given universe, every quantum possibility plays out. The universal wave function evolves smoothly according to Schrödinger's law. Each measurement doesn't collapse the wave, it splits it into independent branches. It's like playing role-playing game like the beloved cult classic Skyrim, in which you reach one of those impossible choices. Spare the monster or kill it. Side with the mages or with the witch hunters. You make your pick, the story branches, and the game continues. In your playthrough, you chose mercy, and the monster lives. But somewhere, in another save file you'll never see, Geralt drew his sword instead. Both stories exist, both are consistent, both follow from the same rules of the game. You just experience one at a time. That idea of branching realities and unseen versions of ourselves didn't stay trapped in physics papers. It leaked into storytelling, especially in film. Directors fell in love with the what-if logic of Everett's many worlds. Every fork in a story became a literal split in reality. Every choice, no matter how small, created an entirely new universe. You see this idea everywhere now. Think of everything everywhere all at once. Evelyn Wang, a tired laundromat owner, is suddenly thrown into a multiverse where every choice she ever made or didn't make created another version of her life in another universe. In one world, she's a kung fu master. In another, a movie star. In yet another, she has hot dogs for fingers. Each branch is absurd, emotional, and deeply human. The film takes Everett's dry quantum concept and turns it into chaos and meaning. All those infinite versions of you, all struggling for purpose. Or look at Mr. Nobody, one of the most haunting explorations of the multiverse ever put on screen. The film opens with a simple, human dilemma. A young boy named Nemo standing on a train platform as it's about to depart. His parents are separating. His mother steps onto the train. His father stays behind. And Nemo hesitates, torn between two impossible choices. Does he run after his mother or stay with his father? In that single heartbeat of indecision, reality fractures. From that point on, Mr. Nobody doesn't follow one life. It follows all of them. We see Nemo grow up in parallel worlds. In one, he becomes a rich businessman trapped in an empty marriage. In another, a drifter searching for meaning. In another still, a scientist chasing the mysteries of time itself. Each timeline unfolds logically from that one moment on the platform, showing how every small choice branches into entirely new versions of reality. The beauty of the film is that it refuses to say which life is the real one. All of them exist simultaneously, overlapping and diverging like quantum possibilities. By the end, Nemo himself starts to realize that there is no single, fixed version of him, just a web of possibilities endlessly branching out. It's a poetic take on Everett's idea. The universe doesn't erase the paths you didn't take. It keeps them all. Somewhere, every version of you is still out there, living the lives you didn't choose. Hollywood loves this idea because it mirrors real life. Everyone wonders about the roads not taken, the job you didn't accept, the person you never called, the dream you walked away from. Everett's multiverse says, none of those paths are lost. They're all still unfolding somewhere, each in its own version of the cosmos. Somewhere in the quantum multiverse, instead of running away, you actually tell your high school crush how you feel. And maybe in that universe, you marry her. And somewhere else, instead of sticking to your 9 to 5, you take a leap of faith and build your own business. And because of that, another version of you is living a life completely different from yours right now. It's a haunting comfort. Every what if you've ever imagined might not be fantasy at all. It might be real, playing out right now in another universe. Not everyone was satisfied, though. Some physicists argued that Everett's branching solved the collapse problem, but left other questions untouched. Why these constants of nature and not others? Why this structure of time and space? That's when new rebels stepped in. In 1992, Lee Smolin proposed something different: cosmic natural selection. He suggested that universes reproduce. Every black hole, he argued, might be a womb for a daughter universe. When it is born, the constants of physics shift slightly. Just as in biology, variations accumulate. Universes more favorable to black hole production generate more offspring. Over cosmic time, the multiverse evolves like species in Darwin's world. Instead of finches with different beaks, we get universes with different laws of physics. Smolin, working at the Perimeter Institute in Canada, often stood against the tide of mainstream string theory. His cosmic Darwinism was bold, controversial, and hard to test, but it extended Everett's idea of branching into the realm of biology. Roger Penrose, the Oxford mathematician knighted for his work in relativity, offered yet another vision. He didn't like inflation and didn't buy Smolin's Darwinism. In the 2000s, he proposed conformal cyclic cosmology. In his picture, our universe is just one aeon in an infinite sequence. As time stretches forward, matter decays, black holes evaporate, and only radiation remains. Once scaled correctly, that featureless sea of light becomes indistinguishable from the beginning of a new Big Bang. In this way, universes don't branch outward like a tree. They flow into one another like pearls threaded on an infinite string. Penrose compared it to the myth of the phoenix, burning to ash only to rise again. Smolin's vision borrowed from biology. Penrose's leaned on geometry and cycles. Both were heirs of Everett in spirit, pushing the boundaries of what a multiverse could mean. Tegmark gathered them all under his shelving system. Whether universes branch, bubble, or cycle, they all follow a logic of multiplication. Reality doesn't settle for one. But for Tegmark, even this was not enough. Branching showed that all quantum outcomes exist. Bubbles explained why constants vary. Cycles suggested eternal rebirth. Yet all of these still belonged to the realm of physics. Tegmark began to wonder if physics itself was just one expression of something deeper. What if reality wasn't built from particles or waves at all, but from mathematics itself? That question would open the door to his most radical level yet. By the time the 2000s arrived, Max Tegmark had already carved out a reputation for himself at MIT. Colleagues respected his technical work in cosmology, but whispered about his taste for bold speculation. Students called him Mad Max, not because he was careless with equations, but because he seemed fearless in asking the kinds of questions that made others uncomfortable. Where most physicists wanted to tighten the screws on models of inflation or refine data from cosmic microwave background experiments, Tegmark wanted to push further. He asked what kind of thing the universe actually is. His answer shocked even the speculative corners of physics. The universe is mathematics. He set down the claim most clearly in his 2014 book, Our Mathematical Universe. The central thesis was blunt. Mathematics does not just describe reality, it is reality. The Schrödinger equation, Einstein's field equations, the Maxwell equations of electromagnetism, they are not useful human inventions that happen to track how nature works. They are themselves the bedrock of existence. The universe is not built from atoms or particles or even energy. It is built from mathematics itself. This claim is what Tegmark called the mathematical universe hypothesis, or MUH for short. The MUH states that every possible mathematical structure exists, not as abstractions in a mathematician's head, but as real universes, each one playing out its own logic. Our universe, with 3 dimensions of space, 1 of time, and laws like quantum mechanics and general relativity, is simply one mathematical structure among countless others. Somewhere else in the mathematical landscape, there could exist universes with 4 spatial dimensions and no time. Or universes whose arithmetic doesn't follow the familiar rules of addition and multiplication, but instead runs on strange modular systems. If it can be defined in mathematics, Tegmark says, then it exists as a universe. What makes this radical is how it dissolves the boundary between physics and mathematics. Physicists traditionally treated their equations as models. They believed the universe had a substance, particles, fields, strings, something. And the math was only the tool for describing it. Tegmark stripped away the substance. There is no hidden layer beneath the math. The math is the thing itself. To make this easier to picture, Tegmark often leaned on analogies. One of his favorites was borrowed from literature. Jorge Luis Borges's Library of Babel, a story from 1941. Borges imagined an infinite library where every possible book existed. Some books contained coherent stories, others were pure gibberish. The librarians inside the story wandered endlessly, sometimes finding meaning, often getting lost in nonsense. Tegmark's mathematical multiverse is like that library, except the shelves are not filled with books, but with mathematical structures. Some universes, like ours, are structured enough to allow chemistry, stars, and eventually conscious beings. Most are sterile, collapsing into incoherence the way most books in Borges's library are unreadable. But all of them exist side by side in the infinite library of mathematics. Tegmark's conviction wasn't only about equations, it came from an aesthetic sense. As a child growing up in Sweden, he was drawn not only to numbers, but to patterns and symmetry. To him, the idea that mathematics is reality wasn't only a scientific proposal, it was a kind of artistic vision. The belief that the ultimate artwork is the structure of existence itself. Our cosmos, with its galaxies and laws, is just one painting in an endless gallery. Tegmark wasn't the only thinker moving in this direction. Around him, other scientists and philosophers were circling similar ideas, though from different angles. Nick Bostrom, a philosopher at Oxford, put forward what became known as the simulation hypothesis in 2003. Bostrom argued that if advanced civilizations ever gained the power to run extremely detailed simulations of reality, then it was statistically likely that we ourselves are inside one. His point was not mystical, but probabilistic. If civilizations can run millions of simulated universes, then most conscious beings will live inside simulations, not at the base layer. The simulation hypothesis doesn't say that mathematics is reality. It says our reality is coded mathematics, like pixels running on a computer. If Tegmark claims the rules of chess exist eternally in mathematics, Bostrom claims we are living inside a specific chess game rendered on a digital board. Meanwhile, physicists working on black holes stumbled on a different but related vision. Gerard 't Hooft in the Netherlands and Leonard Susskind at Stanford developed what became known as the holographic principle in the 1990s. The idea emerged from puzzles about black hole entropy, especially work by Jacob Bekenstein and Stephen Hawking, showing that black holes carry information on their surfaces. Gerard 't Hooft and Susskind pushed further. Maybe the entire universe works like that. What we experience as a three-dimensional cosmos could actually be a projection of information encoded on a two-dimensional surface, like a hologram card that looks three-dimensional but is generated from a flat sheet. Our universe could be a projection of deeper information. Once again, the message was the same. The foundation is not matter, but information, a close cousin to mathematics. Even earlier, a German computer pioneer named Konrad Zuse had planted similar seeds. In 1969, he proposed something he called digital physics. Zuse imagined the universe running like a cellular automaton, a giant computational grid updating step by step. The rules of the grid would be simple, but out of them, complex structures would emerge. Later, Stephen Wolfram popularized similar ideas, pointing to his game of life computer models, where basic binary rules gave rise to patterns resembling organisms, machines, even ecosystems. The suggestion was that the richness of reality could be the product of a simple, discrete computation. At root, the world might be nothing more than bits ticking forward. When you put these visions side by side, a strange harmony appears. Tegmark's mathematical universe, Bostrom's simulation argument, Susskind and Hooft's holographic projection, each of them starts from a different question. yet they all seem to point toward the same unsettling answer. The universe might not be made of matter at all. It might be made of math. Physics, then, becomes a special case of mathematics, just one program running among an infinite library of possible programs. If Everett cracked open the idea of multiple worlds, Tegmark cracked open the idea of what those worlds are made of. Not atoms, not energy, but information itself. The pure, logical architecture from which every possible universe can be computed. For some, this is exhilarating. It offers a sense that the universe is intelligible, that the strange effectiveness of mathematics in physics, something Eugene Wigner once called unreasonable in a 1960 essay, is not unreasonable at all. It is natural because the world is math. For others, it feels like philosophy disguised as science, too speculative to test. Yet even critics admit the mathematical universe hypothesis is not easy to dismiss, because every time physics digs deeper, it finds more math. The language of mathematics doesn't just describe the universe, it seems to be the only language the universe speaks. Tegmark called this final step Level 4, the ultimate layer of the multiverse, the place where not just universes, but the laws of mathematics themselves become real. To understand what makes Level 4 different from the others, imagine climbing a ladder through the previous levels. At Level 1, we're still dealing with familiar territory. An infinite space filled with galaxies that repeat in endless variations. It's the universe of socks and doppelgangers where everything that can happen eventually does, but under the same set of physical laws. At Level 2, we move into stranger territory. Here, each universe is born from its own bubble of inflation, like the ones Linde described. Every bubble may have different physical constants, gravity stronger in one, weaker in another, atoms stable here, but impossible there. Still, they all run on the same underlying mathematics. The equations are the same, only the settings change. Then comes Level 3, Everett's domain, the quantum multiverse. Here, branching worlds emerge from quantum decisions, every possible outcome realized somewhere. Yet all those branches still share one common mathematical framework: quantum mechanics. Level 4 breaks that pattern. It asks a radical question. Why stop at one set of equations? If mathematics itself is the foundation, then why would only our equations be real? Every consistent mathematical structure, every possible set of laws, constants and geometries, should exist as its own universe. Not just variations of ours, but entirely alien realities. Universes with 10 dimensions instead of 3. Universes where time loops or where logic itself works differently. Tegmark calls this the mathematical universe hypothesis. That physical existence and mathematical existence are the same thing. To most physicists, this was an unsettling jump. The earlier levels still dealt with versions of reality we could, in principle, detect or infer. But Level 4 slips beyond experiment. It turns physics into ontology, an argument about what exists. For Tegmark, though, that's the natural endpoint. If math describes reality so perfectly, maybe it's because reality is math. In that sense, Level 4 is not just another rung on the multiverse ladder, it's the foundation beneath the entire structure. The idea that everything, from electrons to galaxies to consciousness itself, is just one of countless possible solutions to the ultimate equation. And that leads to the deepest question of all. If mathematics is reality, then how many realities are there? Every mathematical structure exists as a universe. Every geometry, every algebra, every logical system. The number is not large or even enormous. It is beyond counting. The multiverse, in Tegmark's view, is not just vast, but absolute. It contains everything that can be defined. And that realization forces us to confront a haunting possibility. Our universe is only one sentence in an infinite library of reality.